Now we get the definition for current space and null space. It's time to introduce how to find them in a systematic approach. So for the null space, let's consider this problem. This A is 3 by 4. 3 rows, 4 columns, meaning 3 equations for 4 variables. At a first glance, it's impossible to get unique solution, right? Because you have one more variable to go. So in this case, before we consider the right-hand side, this structure of A already determines the degree of freedom we can set. It's not like once the solution is not unique, we have all the solution in the world. No, we have to find the rules between these numerous solution. And the whole process begins by Gaussian elimination. Everything starts by Gaussian elimination. And that's why I keep emphasizing how this approach affects the whole linear algebra. Okay, so for this A, the standard Gaussian elimination approach start by locating a first row, and when we multiply the first row by -2 and add it to the second row, we get 0, 0, 3, 3, with -1, -3, 3, 4 here. So clearly, the next step is to use the first row one more time and multiply this by 1 and add it to the third, which produces 0, 0, 6, 6. And the last approach is observe this structure where 1 is pivot. This 0 is not pivot. The 3 becomes the pivot for the second row. So we need this to do a further round of row manipulation. So we multiply the second row by -2 and add it to the third, which gives the last row a full 0. So finally, we have only 2 pivots, 1, 0, 0, and 3, 3, 0. This structure is still like an upper triangular matrix, but we cannot call this upper triangular matrix. This term is limited to only the square case. We call this row echelon form because these non-zero entries sit into an echelon style. So a row echelon form for you, it uses the same notation. It's just we cannot call it upper triangular matrix. However, the way that we get this upper triangular matrix, a row echelon form is still an actual lower triangular matrix, a square and lower triangular matrix. Such an L, if we use A equals LU, the L will be, it can be found by all those row manipulation. It's 1, 1, 1, 2, 1, 0, -1, 2, 0, 0, 0. It's still an actual square and lower triangular matrix. Okay, so we still have a rectangular version for A equals LU. With the U here, we can do further manipulation. First of all, those columns containing pivots are called pivot column. The term won't lie. It already shows that these columns are more important than others. That's why they are called pivot columns. The remaining columns are called free columns, including this one. and this one, the second and the last, free column. As it is a 3 equations, 4 variables question. So the 2 variables associated with pivot columns are further called pivot variable. This includes x1 and x3. They are pivot variable. On the other hand, x2 and x4 are known as free variables, which are associated with free columns. So far, we still apply the standard Gaussian elimination and identify some more information from it. Pivot columns, pivot variables, free columns, and free variable. And here comes the most essential steps in null space. Express the key pivot variables in terms of the free variable. For the third equation, everything is 0. But for the second equation, we can have 3x2, 3x3 plus 3x4 equals 0. So we make the pivot variable be expressed as the free variable, x3 be minus x2. So let me circle a pivot and pivot variables one more time. Once we have done that, we can do the first equation, which is x1 plus 3x2 plus 3x3 plus 2x4 equals 0. So with x3 equals minus x4, this becomes minus x4, or minus 3x4, which get positive x4 here. So x1 becomes minus 3x2 minus x4. And x3 equals x4. So with x3 substituted by minus x4, and x1 be minus 3x2 minus x4. This is a positive x4, I beg your pardon. So with x1 and x3 be substituted into in terms of the free variable. Finally, the x that makes ax equals 0 becomes this vector by separating x2 and x4. x2 times minus 3, 1, 0, 0 plus x4 times 1, 0, minus 1, 1 will make ax equal 0. And when we perform Gaussian elimination, which makes a be u, we didn't change the structure for those variables. So the x that makes ax equals 0 will also make gx equals 0. So actually, we use the last equation, gx equals 0, to determine the null space vector. And finally, the x that makes gx equals 0 is these guys. x2 times minus 3, 1, 0, 0 plus x4 times 1, 0, minus 1, 0. So these are our null space vectors. In other words, the null space vectors is the linear combination of 2 vectors from R4, including minus 3, 1, 0, 0, and 1, 0, minus 1, 1. There are 2 vectors. Their combination becomes the null space. So the null space dimension in this case is R2. It's a plane within R4 space, a 2-dimensional plane which is formed by minus 3, 1, 0, 0 and 1, 0, minus 1, 0 and 1, 0, minus 1, 1 which locates inside an R4 space. So that's the formal process in finding null space basis. In null space vector, not yet basis. I'll talk about basis later. The dimension of null space is determined by the number of free variable. In this problem, there are two free variables. That's why the null space dimension is R2. This R2, the dimension for null space, affects a lot of useful conclusion. So we give it a new index. We call this nullity. Nullity, yeah. Finally, let's go back to the complete solution for AX equal B. In the whole process, we first identify uniqueness from the null space vector. If you have free variable, then you must have infinite numbers of solutions. The solution cannot be unique. Even we know that, we don't know the complete solution yet. We only know we have plenty of guys in the null space. And to determine the complete solution, this relies on the right-hand side. The right-hand side is originally B1, B2, and B3. So if you put this B along with A as an augmented matrix, we perform those Gaussian elimination steps. With B considered, this leads us to U and C, the right-hand side, which in this case, B1, B2 minus 2B1, B3 minus 2B2 plus 5B1. And as you can see, these coefficients can be found in L. Yeah, the L also determines those coefficients. It's nature, because when you apply the Gaussian elimination for A and B, the L inverse A brings A to U, and L inverse B becomes the right-hand side, whereas B is a 3x1 vector. So the L inverse can be found using this structure: 1 minus 2, 5, 0, 1, minus 2, and 1. The L inverse. Okay. So we need to assign some proper value so that we have a solution. But how do we assign the B1, B2, and B3 so that we have a solution? The B1, B2, and B3 must be the linear combination of the columns in A, which means that B is on the column space of A. Considering 1, 5, 5, is there a solution from this? Yeah. An obvious choice is, once this guy is not 0, it's hopeless to get a solution. The interpretation for this right-hand side is 0x1 plus 0x2 plus 0x3 plus 0x4, which must be 0, of course. Yeah. So consider 1, 5, 5. Yeah, it can make this works. The right-hand side will be 0. So let's consider this 155. Would 155 lead to a unique solution for this? From the right-hand side here, the first entry is 1, the second entry is 3, and the last entry is purposely 0. So from each equation, x1 plus 3x2 plus 3x3 plus 2x4 equals 1, whereas 3x3 plus 3x4 equals 3. So similarly, let's make everything be expressed as the function of only free variable. So x3 will be 1 minus x4, and x1 will be 1 minus 3x2 minus 3 plus 3x4 plus minus 2x4, which is minus 2 minus 3x2 plus x4. So once we express x1, x2, x3, and x4 as a matrix form, it becomes minus 2 0, 1, 0 plus x2 times minus 3, 1, 0, 0 plus x4 times that second vector 1, 0, minus 1, 1. The first solution or the first term is further called particular solution because this one exists because of the B155. The remaining two vectors, this combination is known as null space solution. Xn, they are not affected by B. They are always there. Once you have A, you have a null space solution already. This further means that when we deal with an AX equal B problem, we separate the solution into particular components and a null space component because only that XP produce the non-zero B on the right hand side. But even though you have a SP as solution, there is already Xn, which makes AXn equals 0. So you cannot take only the B part, the mapping to the B part, XP, into account. Xn is always there. So the overall solution is XP plus Xn. In other words, we can tell the particular solution from B once B is on the current space. At this stage, we interpret the current space using the zero row. If a row is full of 0, then the condition to get that 0 right hand side is B3 minus 2B2 plus by B1 equals 0. We will have a different way later. However, current space explains existence of solution, yet null space may provide information about uniqueness. The title for this section is Existence and Uniqueness of a Solution, and now we understand why they are associated with current space and null space. You can see the null space from the uniqueness, and you can get the existence of solution from investigating the current space. So we start by AX equal B. We gradually turn the system into UX equals C. UX equals C is already good. We can get all the stuff we need from UX equals C. However, linear algebra just evolves the system into another form. It's like when A equals LU, you can already identify pivots, rank from U, but I don't know the reason. Maybe it could be cleaner or what. Mathematicians in linear algebra insist in A equals L du so that you can see D for those pivots. Similarly, you can already tell us the pivot variables and the free variable. Mathematicians didn't stop here. It evolves UX equals C into RX equal D, whereas you can see all the information here from UX equals C. So the RX equal D form means the pivot columns can be only identity matrix, which means it's either 1 or 0. It can have at most 1, 1, and all the other entries are 0. So if you extract the pivot columns, they will be formed like identity matrix, and the remaining columns are from free variables. We don't do anything about it. They are just there. So the goal for R is to make the pivots clearer. The pivot can be seen using this because all the coefficients be 1. And yeah, there is indeed some benefits from Rx equal D. For example, the substitution for free variables would be easier. Oh, by the way, how do we get R from U? Still, the only thing we did so far, row operation. You first make the second row be divided by 1. No, divided by 3. So this is 1 and 1. And then backward elimination. You multiply this row by minus 3 and add it to the first row. So the first row becomes 1, 3, and more importantly, 0 here, where minus 1 are the last entry. So this produces an R structure where you can see the conversion of free variables and pivot variable easier. For example, from the second equation, x3 plus x4 equals 0. So x4 can be readily substituted by minus x3. And you don't have to substitute this into the first equation anymore, because the first equation, which is x1 plus 3x2 minus x4 equals 0, can be x1 equals minus 3x2 plus x4 directly. So no more substitution from second equation, and we can get the full solution for null space in an easier way actually. And as you can see, from U or R, we can see the number of free variables easily, and they must be the same as the null space of A, the free variable of A. But it's challenging to see the number of free variable directly in A, unless it's a design case like this one. Okay, so if we transpose the whole system, it's originally 3 rows, 4 columns. Now, please check the A information. I make the columns be row, the rows be columns. Almost the same. But what if I make A be transposed? Does this affect the number of free variable? Does this affect the rank? The size is already different. A is 3 by 4, but A transpose is 4 by 3. So the size already tells us something different. If we perform Gaussian elimination for this one, you will get, I just provide the U directly without the detailed process. So the U in this case will be 1, 2, minus 1, 0, 0, 0, because the second row is 2 times the first, and 0, 1, oh no, 0, 3, 6, 0, 0, 0 here. Yeah, this is the structure of U. So this columns contains pivot variable. This column also contains pivot variable. Yeah, but can we stop here with 3, 6 consider? Yeah, 3 is the pivot. So this one is also pivot variable. This figure tells us the rank, which means the number of pivots, is still 2, just like the original case. And this is not coincidence. In the next section, we'll introduce more formally, but here we already see that the transpose won't affect the rank. A and A transpose have the same rank. Remember what rank means? Yeah, the number of pivots, I get it. But this also means there are 2 independent columns illustrated in A. When we transpose the matrix, we make the columns be row. So A transpose means we have two independent columns in A transpose, which also means we have two independent rows in A. So this becomes something big because the number of independent columns will be the number of independent rows. When we apply Gaussian elimination, we aim at pivot columns and free columns. We focus on only columns, but the number of independent columns will always be the independent row, number of independent row. But the number of free variable is of course different as there are only 3 columns. Pivot takes 2 columns, so we have only 1 free variable. Yeah, so the first question is about what conditions on B make the system solvable. We have to make B be on the column space of U, which will be the column space of A. What I just said is incorrect. Yeah, B must be in the column space of A, but the column space of A won't be the column space of U. I'll talk about this later. Yeah. However, from here, if we take B into the as a augmented matrix, the right hand side will be B1, B2 minus 3B1, B3 minus 3B1, and B4 minus 3B3 plus B1. Yeah. So to make the solution solvable, those 0 rows must be matched to 0 for the right hand side. So first of all, B2 minus 3B1 is 0. Secondly, B4 minus 3B3 plus B1 is also 0. So that's the conditions to have 0 for the right hand side. But how about the associated solution for X in terms of B1, B2, B3, and B4? Yeah, it cannot be done without identifying the null space. So from the second equation, 3x2 plus 6x3 equals 0, which means x2 is minus 2x3. And from the first, 1x1 plus 2x2 minus 1x3 equals 0. So x1 will be 5x3. In other words, the null space solution is x3 multiplied by 5 minus 2 and 1. Yeah, this is the xn part. As for the xb, yeah, we have to make the x be in terms of b. So following the ux equals c problem, where 1x1 plus 2x2 minus 1x3 equals b1, and 0 plus 0 times x1 plus 3 times x2 plus 6 times x3 b3 minus 3b1. So you do the math, you can get the xp part be 3b1 minus 2/3 b3 and 0 1/3 b3 minus b1. Yeah, and the overall solution is xp plus xn. Rank tell us a lot of useful information. We can tell, first of all, the number of pivots from the rank. Rank is the number of pivots, and it tells us the number of linearly independent columns. It also tells us the number of linearly independent rows. And the number of free variables is found by n minus r, the total variable n minus r. So the number of pivots is called the rank, and if we have a M by N matrix, yeah, there are three special cases. Yeah, first of all, if R is just M, for example, M greater than M, N meaning more rows, less column, and once R is already M, you could have, let me add an equality sign, you could have free variable or not. We don't care. But when R is already M, yeah, there is no more zero row. Yeah, if we go back to all the previous scenario, the conditions to have a solution is B must be on the current space, right? This further means that the zero rows in U must be matched to zero. So we keep finding these conditions. Yet, in this case, if R is M, if there is no more zero rows, we don't have to bother whether there is a solution. It always has a solution. No more zero row. This also means that the right-hand side B can always be expressed as the linear combination of columns. So when R equals M, always solvable. We always have a solution. When R equals N, oh, by the way, can we have a tall matrix? This is called tall matrix if more rows, less columns, less columns. And this is called Y matrix. More columns, less rows. Can R equals M be a tall matrix? No, because remember, the number of independent columns will always be the number of independent rows. So if it is a tall matrix where you have more rows than the number of columns, how can R be M? M greater than N, right? Yeah, this is the case of M smaller than N. But considering a tall matrix, the number of rows is greater than the number of N. When R reaches N, stop. Yeah, this must be stop. R cannot be scaled up to M. So R equals M scenario should limit it to only Y matrix. When R equals N, this is a case that no free variable. So you may have unique solution once right hand side is on the current space of A. So for R equals N, it's more like a tall matrix. Yeah, this could more be a tall matrix because for Y matrix, can you have R equals N for Y matrix? R equals N for Y matrix. Can this be done? No way. When M is smaller than, when M is greater than N, then R equals N stops. It cannot move on. So R equals N is only for tall matrix. It's never for Y matrix. And when R equals N, it means you have no more free variables. So you can have a solution. And once you have a solution, it must be unique solution. And you could have no solution at all if B is not on the current space. So considering this case, R equals M equals N, which means that it must be square, which also indicates the rank is the number of rows and the number of columns. So you must include the previous two stuffs, including it's always solvable. The solution is always unique. So this is the best case you can get. You have a solution and that solution is a unique solution. With this understanding, now we can use more formal languages about the four fundamental subspaces. This requires some terminologies. Independence, spanning, basis, and dimension. Yeah. This illustration already shows the logic. Basic is placed as the center. It governs all the concepts, and basis lead to the so-called dimension for subspace. I must clarify that it's for subspace. Perhaps you are wondering, we already see the dimension for subspace, like the dimension for the null space is R2 in previous examples, and the dimension for the current space can be found in some other ways. We haven't formally introduced dimension for subspace. That's all our intuitive understanding, not a formal way, because you cannot have dimension without understanding the basis. Finding the basis is the first. But basis cannot be found without investigating the independence and spanning among vectors. So the slides once again shows us the definition for linearly independence. If these vectors are independent, then C1v1 plus C2v2 up to CKvk be zero, only come from zero for those coefficients, right? We already know this. Yeah. Considering this case, 2, 4 minus 2, 1 minus 6, 7, 1, 6, 2, are they independent? We don't know, or we know, but we need some computations for it. Yeah, we still have an approach to judge it, but it needs some more rounds of computation, and that some more rounds of computations are Gaussian elimination. We can put them as a matrix. By performing Gaussian elimination, we can see whether they are independent, and in this case, they are 2, 0, 0, 1 minus 8, 0, and 1 minus 2, 1. I know that because I select this purposely. From U, it's super easy to judge whether 2, 0, 0, 1 minus 8, 0, and 1 minus 2, 1 be independent. They are, as the only way to make 0 as the combination come from 0 times this plus 0 times the second column plus 0 times the third column, or else you cannot turn the last entries into 0. But how about 2, 4 minus 2 and 3, 0, 0, 0? Are they independent? If 0 is your vector, then nothing is independent for it, because yeah, you can multiply this vector by any scalar, and 0 times this guy plus c times this guy will always be 0. How about 4 three-dimensional vectors be independent? Can we choose 4 vectors from R3 space be independent? No, never. Yeah, because this will get a Y matrix. 2, 4 minus 2 here, 1 minus 6 here, 1, 0, 2 here, 3, 4, 5 here. Even there are 3 independent vectors, the last one must be the linear combination from the previous 3. So no, it's not the case for linear independent. So you cannot choose more numbers of vectors than that dimension of the space. If your dimension in a space is Rm, yeah, you can choose at most m independent vectors. Any m plus 1 vector must be the linear combination of the previous m vectors. So identify pivot column is always important. They tell us the position for the pivot columns, and the free columns must be some sorts of linear independent from the pivot column. And if all columns are linearly independent, the situation for the null space is are 0. And remember, you can never say that we don't have a null space. Even though all the columns are independent, you still have a null space. 0 will always be your null space, the trivial solution. The next one is, if the column vectors are linearly dependent, what is the situation with the null space? Yeah, there must be non-trivial one. And if there are free columns in U, what is the dependency between free columns and pivot column? We can substitute the pivot in terms of free column, in terms of free variable. This is like the way that we find those free variables and the null space vector. So when R equals n, the column vectors are independent. So this is the first term we need to define the center in this section, or even the whole short course basis. And the next term is called spanning a subspace. If a vector space V consists of all linear combination of particular vectors V1, V2 to Vk, then we call this vector span the subspace. In other words, span means linear combination. The independence concerning the essence, the value out of several vectors. I mean, if you have 100 vectors, don't treat them like equally important. They are not equally important. Some are more important than others. Which are more important? Pivot columns. Express them as a matrix and perform the Gaussian elimination. So for 100 vectors, the mindset is to identify the pivot columns. The pivot columns will be more important than others. And the underlying reason is, once you find the pivot columns, everything are just the extension of it. They are linear combination for it. So the independence is like summarizing the information into the essence. It focuses on excluding unimportant parts, providing the essence out of those vectors, the information. Span is another thing. This is completely different. This is like the opposite of independence. Span is, if you have like 4 vectors, you may consider that, oh, one vector is what? Second vector, third vector, and fourth vector. You think you have only 4 vectors. That's not true. You have all the vectors in the world. You have the linear combination of these vectors. These vectors, the linear combination of the 4 vectors at hand are all the information you have. Your information is not limited to those 4. The linear combination can be derived from them. So span means extension. Independent means summarization out of some trace information, and span is to extend our information into something bigger. Yes, it's just another word for linear combination, but now we can use this formal term to call linear combination. Yeah, actually, for the past parts, I already mentioned span once, and I regret for it. I should use linear combination because this is the formal time that we introduce span or spanning. So the current space of A means you identify some vectors only, but this vector can span the whole subspace. The current space is spanned by those column vector. And the null space of A is spanned by the X that makes AX be 0. So the null space is still spanned by only few vector, but those few vector provide you the whole subspace. So now we can compare the two information together, the two concepts. One focus on we would like to reduce the information from many vectors, and span focus on we would like to extend the information from only few vectors. A basis for a vector space is a set of vectors that show both independence and spanning. In other words, we have not too much vectors and not too few vectors. Yeah, we have right what we need to define the whole subspace. If you remove one vectors, you cannot span the whole subspace. If you add one more vector, they are no longer independent. So in this status, it clearly fulfills the whole subspace. You cannot remove one and you cannot add one to break the independency. We call this basis. Yeah, a basis is a maximal independent set and also a minimal spanning set of vector. Not too many vector, not too few vectors. When you have a subspace, basis will not be unique. There will be numerous ways to define a vector space. Yeah. So when I assign examinations about finding a basis, I have to check the solution provided by students carefully, because maybe students A, student B, student C, they all provide different bases, yet they are all correct. So there will be more ways to find the basis for a subspace, but the number of vectors in that basis is unique. That must be there, because you cannot add one more or remove one. Basis is the ID of a subspace. In linear algebra, we always find a basis. If you have a subspace, the first thing you did is to find a basis. Why? Because when you find a basis, you have the whole subspace, as the subspace is spanned by the vectors in the basis. So you find the basis, you find the whole subspace. And the basis contains only independent vectors. So that's the correct way to present a subspace. Yeah. So my point is, basis is a method to describe a subspace. In a subspace, there are just too many vectors. There are countless vectors if you treat them as individuals. But when you can find the basis, if you can determine the basis that is correct for this subspace, the linear combination, the span of these vectors is that subspace. With the basis at hand, now we can finally introduce the formal definition for dimension. The dimension of a vector space or vector subspace is the number of vectors in a basis. Yeah, it's not like, let me tell you what we did before and what is different at this stage. Everybody knows this vector is from R4, and the reason to call it R4 is to count the number of entries. Yeah, this is not incorrect, but it has confusion because this vector is one line in R4. So if the vector forms a subspace, this subspace is R1. So from only one single vector, we need to figure out, are we concerning the space or the subspace? But now, if your goal is to have the definition for R4, this means you must have 4 vectors and only 4 vectors, like this, yeah, it becomes the basis for R4 because every vector can be found as the linear combination for it. It's just a problem about finding those coefficients, but all the vectors are the linear combination from the 4 vectors. Similarly, if your space is spanned by only one vector, it's R1, and that vector becomes the basis. So we can count the number of bases, the number of vectors in the basis to determine the dimension. It becomes the formal way to determine the dimension. So remember, yeah, these terms could be incorrectly used. There's no such thing as basis of a matrix. Basis is for subspace. We can call finding the basis of a subspace, but not finding the basis of a matrix. Rank is something for matrix, so there is no such thing as rank for a space. Rank is for matrix. And then dimension of a basis is also, or dimension of a basis is incorrect. Dimension is for space or subspace, not for basis, not for matrix. That's why I said the size of a matrix, the size of a matrix instead of the matrix, the dimension of a matrix. The dimension is for space or subspace.